Hello students, in this session let us solve one more question of simply supported beam. In this question it is given that a simply supported beam of length 10 meter carries the uniformly distributed load and 2-point loads as shown. Draw the shear force and bending moment diagram for the beam. Also calculate the maximum bending moment. So this is a question of simply supported beam. We are given with 50 kilonewton and 40 kilonewton point loads. Also there is a UDL of 10 kilonewton per meter which spans over a length of 4 meter. The total length of the beam is 10 meters. We have to draw the shear force and bending moment diagram. Let us solve this problem. This is the simply supported beam at which a UDL is there at some part of the beam. It is not at the entire part of the beam. In theory we have studied the UDL with entire part of the beam, simply supported beam. Here the UDL is at only limited part 4 meter, and also along with UDL there are 2 point loads are there, 50 kilonewton and 40 kilonewton, and we have to find out, we have to draw the shear force diagram and bending moment diagram for this question, right? So let us solve this question. First of all, we have to find out the reactions at support A and B. First find out the reactions and then we will proceed, right? So what is reaction at A? Suppose this is RA, and what is reaction at B? Suppose this is RB. First of all, find out RA and RB. Take moment of all the forces about A. This is UDL and it will be having a 40 kilonewton of load. 40 kilonewton of load at the center, at this point, at the center. Why 40? Because 10 kilonewton per meter is the linear force density, and if linear force density is 10 multiplied by 4, it will become 10 multiplied by 4, 40 kilonewton, right? That's why we are written 40 kilonewton at the center. Now, how many forces are there? RA is one force, RB is another force, 2 forces are the reactions, and 3 forces are this, 50 kilonewton, 40 kilonewton, and this 40 kilonewton, which is the concentrated load of this UDL at the center of this C and D, at the center of CD, right? So 3 are the downward forces and 2 are the upward forces. Take the reaction of RA. The reaction of RA about A will be equal to 0. Take the reaction of this 50 kilonewton. So sum of all moments about A should be equal to 0. So this will give, what is going to this? 50 multiplied by 2, let us take positive it, 50 multiplied by 2, 50 multiplied by 2, 40 multiplied by 6 plus 40 multiplied by 6 plus this 40, which is the concentrated load of UDL, 40 multiplied by 2 plus 2 because it is the center of C and D, so 4, so 40 multiplied by 4, and then RB, which is minus, RB multiplied by total distance, it is 10, minus RB multiplied by 10. So from here we can find out RB. So from here RB can be found out that RB will be equal to, solve it and you will get, this is 50 multiplied to 100, 240, 160, and then this is RB multiplied by 10. So RB will come out to be 50 kilonewton. So RB will come out to be 50 kilonewton. So this one equation we have obtained, that RB is 50 kilonewton. So RB is 50. Now we want to find out RA. All the vertical forces, sum of all the vertical forces should be equal to 0. So sigma F vertical should be equal to 0. So this will give that RA plus RB, which are the vertically upward force, should be equal to vertically downward forces, 50 plus 40 plus 40, 50 plus 40 plus 40. Solve it and you will get the value of RA. Solve it and you will get the value of RA. The RA value will come out to be 80 kilonewton. 80 kilonewton. So we have obtained the value of RA also. So we have calculated the value of RA and RB, taking the moment at A and then the sigma FV equal to 0. So we have obtained the value of RA and RB, right? So this is the one part of this question. We have found out reaction. So reactions are 80 kilonewton at one end and 50 kilonewton at the other end by using this concept, right? Isn't it? Now, second part, finding the shear force. Shear force of this simply supported beam. We have to take the sections at different points. We have to take the sections. So take the sections. Let us take first section as between A and C, then second section between C to D, and then third section between D to B. We have to take the three sections, right? So let us take first section, say this, which is at a distance x, from free end, and this is suppose capital X. So this section is at a distance x from the free end, one end. So simply supported beam, this is a one end x distance, right, between A and C. So what is the force? Fx. Fx will come out to be the all the forces to the left of the section, and upward it is taken as positive. So this is RA only, right? No other force is there. So this will be equal to RA, and this is positive, and which is equal to 80 kilonewton, and which is valid between A to C. So this is valid between A to C. 80 kilonewton of positive load, right? So at FA, this will be equal to FA at what distance? FA, the x value is 0, and this will come out to be 80 kilonewton because load is same. And what is FC? FC at a distance of 2 meters, x is equal to 2 meters, and this will again be 80 kilonewton because the force is same, right? So find out, draw now the diagram. Draw the diagram now. 80 kilonewton. So this is suppose 80 kilonewton. This is 80 kilonewton, and draw the 80 kilonewton force from here to here. So this much distance is 80 kilonewton, right? So this point is basically 80 kilonewton point. 80 kilonewton. This entire line contains the load of 80 kilonewton, right? Now this is one part. Now take one more section. Let us take one more section. Say we can take section here. We can take section here like this at a distance of suppose x1 from point A. This distance is x1, like this, x1 distance from A. Take a section x1 at a distance of x1 from A, right? This section, name it as x1. Suppose this section is x1. Now take the force at x1. What are the forces are there? There are three forces. One is 80 kilonewton, another is 50 kilonewton, and one more force will be there. That is this part of UDL, this part of UDL, which will be having a load of 10 multiplied by x. Total 10 multiplied by, this part is different. This part is 10 multiplied by x1 minus 2, right? So this will be having a concentrated load of this part of UDL, that is 10 multiplied by 10 is the load multiplied by distance. This distance is very small distance, Cx1, and Cx1 is x1 minus 2. This is x1 minus 2. So this is a load. There are three loads are there. One is Re, another is 50 kilonewton, and another is 10 multiplied x1 minus 2. X1 is this distance and 2 is this distance. So Cx1 distance will be x1 minus 2, and it is multiplied with this linear force density, and we will get 10 into x1 minus 2, right? So Fx1 will be equal to forces to the left of this section, that is 80 minus 50 minus 10 multiplied by x1 minus 2, right? And this is valid between C to D. 80 minus 50 minus 10 multiplied by x1 minus 2, which is the part of UDL. This is the some part of UDL, that is Cx1. This is the Cx1 part of the UDL. Cx1, which is 10 x1 minus 2 is distance and 10 is the load density. And this is a linear equation. Then what is the value of F at C? Value of F at C, that is equal to x1 when the x1 is 2 meters. Put here the value of x1 as 2 meter, you will get 80 minus 50 as 30 kilonewton, right? And what is FD, which is at a distance of 6 meters, where x1 is equal to 6 meters. What is FD? Put here 6 meters, so you will get 6 minus 2 4, this is 40, 50 and 40 90, minus 10, so this is minus 10 kilonewton. Put here and you will get the value as minus 10 kilonewton, right? So this is a linear variation from 30 kilonewton to minus 10 kilonewton. From C to D, variation is 30 kilonewton to minus 10 kilonewton, right? So from C, this is the C, and from C to D in negative direction, like suppose this is 10, and from 30, this is 30, say this is 30, right? From 30 to 10, say this is 10, and linear variation is there. This is a linear variation from 30 to 10, like this, right? This is 30 kilonewton, and this is 10 kilonewton. From 30 to 10, there is a linear variation. Next is between D to B. Again take the section. We can take section from left or we can take the section from right. It is better to take the section from right because in right there is only one force is there. So we can take this section from right itself, like this. From right. We are taking section from right now. And this is suppose x2. Remember that x2 is from B, not from A. It is from B. Now we are taking from B, right? Remember that we are taking from B for the ease of calculation, because otherwise we have to consider all the forces. Now we have to consider only one force, that is 50 kilonewton, right? So that's why we are taking the right section now, not the left section. So shear force will be sum of all the forces to the right of the section, and this is 50 kilonewton, and this is rightward upward, which is negative, so minus 50 will come out to be, right? So Fx2 will be equal to minus 50 kilonewton. This is RB only, right? RB, right? I can write here RB. This is RB, which is equal to minus 50 kilonewton, and this is valid from B to D. It is valid from B to D, right? So from B to D, it is minus 50 kilonewton, and it is constant. So at FB, which is at a distance of x is equal to 0, x2 equal to 0, this is same minus 50 kilonewton, and at D, which is at a distance of 4 meters, This is again minus 50 kilonewton. So now we are drawing from here, starting from here. This is minus 50 and this is minus 50 is constant from here to here like this. So this part is 50 kilonewton and here it is positive and here it is negative, right? So this is A, here somewhere C, and this is D, and this is part B, right? So this part is 50 kilonewton, this is 80 kilonewton, and then 30 and 10, right? So this is the shear force diagram for this beam, shear force diagram, right? So at peak points A and B, the values are 80 kilonewton and minus 50 kilonewton. So this is the shear force diagram for this question, shear force diagram. Bending moment diagram. So let us draw here the bending moment diagram of this. Bending moment diagram. This is our reference line A, C, and D and B, right? And here we want to draw the bending moment diagram, right? So take the section X, let us take X and find out the moment of X, mx. That is the moment of all the forces to the left of the section. 80 multiplied by X, so that is, and this is positive, 80x, this is positive. So this is 80x and valid between A to C, valid between A to C. And what is MA at a distance of X is equal to 0? Put X is equal to 0, linear variation is there, but mx it is 0. And what is MC, which is at a distance of X equal to 2 meters. Put here 2 meters, you will get 160 kilonewton meter. From 0 to 160 kilonewton meter, linear variation is there, right? 0 to 160. So 0 to, suppose this is 160. So 0 to 160 linear variation is there like this, right? 0 to 160. And this point is of 160 kilonewton meter. Isn't it? Right. And linear variation is there. So this is the one part. Next part is from C to D. So take section from C to D. We have already taken section X1. X1 section is already taken, right? So mx1, find out mx1, that will be equal to moment of all the forces. Here 3 forces will be there. We have to take the moment of 3 forces about x1. One is 80, which is Ra, another is 50, which is at point C, and another is this, some part of UDL, Cx1 part of UDL, which is 10 x1 minus x2, and at a distance of center, it is at a center of Cx1. It is at the center of Cx1, right? So we have to take the moment of 3 forces. 80 multiplied by x1, and it is positive, 80x1. 50 multiplied by x1 minus 2, x1 minus 2. So minus 50, x1 minus 2. This is a moment of 50. Minus because it is anti-clockwise direction in leftward side. So x1 minus 2, right? And then moment of this force, right? This force. I am making it in a Q rectangle like this. 10 x1 minus 2. This is another force, this part of UDL, right? 10 x1 minus 2. And this is at a distance, it is at a center of this. So it will be Cx1 distance must be known. We know that Cx1 distance is x1 minus 2. Half of this will be the distance of this load from x1, right? So we will write minus 10 x1 minus 2, 10 x1 minus 2 at a distance of this distance is Cx1. Cx1 is x1 minus 2 divided by 2, like this, right? So this is the bending moment. This is the bending moment at x1, right? So you can further solve it if you want to solve that. mx1 is given by 80x1 minus 50 x1 minus 2 minus 5 x1 minus 2 whole square, right? And this is valid between C to D, between point C to D. This equation is valid between C to D, right? So what is the value at C and what is valued at D? So m at C at a distance of 2 meters, what is the value? Put here 2 meter, 2 meter, 2 meter, you will get 160 kilonewton, 160 kilonewton again. And what is the value at D, md, at x1 is equal to md, 2 plus 4, 6 meters, 6 meters. So what is the value when x1 is equal to 6? Put here 6, 6 and 6, got the value, use calculator and get the value, and you will get the value as 200 kilonewton meter, 200 kilometer, right? So it means that here at D point there is some value 200 greater than this. This is, suppose this is the 200. So from 160 to 200, this was 160, and from 160 to 200 kilonewton meter, it is increasing. But you will get somewhere here the maxima. You know that where the point where shear force is 0, the bending moment is maximum. So at this point, say this is E point. So at this point, E point, you will be getting maximum bending moment, E point. So maximum bending moment. So you have to draw the diagram such that the peak should come here, like this. Yes. And this is a parabolic curve, you can see here, this is a parabola. So you will get this type of curve, from linear curve to parabolic curve, right? Where peak is here, maxima is here, at this point, right? This point. So maxima is at this point, right? So this is the M max. Isn't it? This value, M max. And for M max, the shear force should be equal to 0. So let us find out later on what is the value of M max. So here, now proceed further, later on we will do it. Proceed further from D to B. What is happening between D to B? And we have to find this maxima also. What is the maximum value of bending moment? We will find out. If they are asking, we can find out the maximum bending moment also. So from 160 to 200 in a parabolic manner, first increasing, then decreasing, because maxima is at this point, E point. This point is the maximum point, maximum bending moment, right? Now third, from D to B. This was valid from C to D, now from D to B. D to B. So mx2. We have taken mx2 from this side, from B. From where you can take, from anywhere you can take, we are taking from right section. So this is mx2 will be equal to moment of 50. So moment of 50 will be, and this is positive again, so this is 50 x2, and we can find out 50 x2, and this will be valid between B to D, from B to D. So what is the value at B? At B, the value of x2 is 0. Put here 0, you will get 0 value. And at D, where x2 is 4 meter, put value 4, we will get 200 kilonewton meter. Right? So from 0 to 200 kilometer in a linear fashion. So this is again a linear curve. You will get again a linear curve from here to here, like this. So this point is 200 kilonewton meter, and from here to a linear curve. So from A to C it is 160 increasing, then it is a parabolic curve, and then again is a linear curve, right? So this is how we draw the bending moment diagram. So this is the bending moment diagram, right? So we have divided this into 3 sections and then we have solved it, right, and drawn the bending moment diagram. But what is the maximum bending moment? Maximum bending moment. For maximum bending moment, we have to find out the location where the maximum bending moment is acting between C and D, and this curve was valid between C to D. But what is the value of x? This x1, where the bending moment is maximum. What is that value? That point where this bending moment is maximum, or shear force is 0. So we have to go back for that. And find out the shear force between C and D. And put the value of shear force 0, we will get the value of E, the location where this AE, where this bending moment shear force is 0. So what is shear force between C and D? So we have to find out shear force equation for C to D. Shear force equation again we have to find out between C to D. We have rubbed that. So shear force equation for C to D. So for C to D there are 3 forces are there, RA, 50 and this. So shear force Fx1 at x1 is a section between C and D, at x1 will be equal to 80 minus 50, 80 upward is positive, 50 downward, and then this minus 10 multiplied by x1 minus 2, right? And we want to locate this point E, and for E this should be equal to 0, right? Because we know Fe equal to 0. So for locating the E, let us find out this, and this is 30 and 3 and 2, 5. So you will get x1 equal to 5. From here you will get the value of x1 is equal to 5 meters. So from A this E location is 5 meter at a length of 5 meter. So this E point is at a distance of 5 meters from A. This distance is 5 meters basically, at which the shear force is 0 or bending moment is maximum, right? So if this is the case that this is the point where E is maxima, bending moment is maxima, so put the value of x1 in this equation, right, which is valid between C and D, right, and then find out the maximum bending moment, Mmax. So Mmax will be equal to put in this value Mx1, 80 multiplied by 5, 80 x1, so 80 multiplied by 5 minus 50 x1 minus 2, 5 minus 2 minus 5 minus 2 square. So from this you will get Mmax. Solve it and you will get the maximum bending moment, and this will lie in this part. Why in this part? Because this bending moment equation was for C and D, right? So this will lie in this part only. This part we are utilizing this equation for maximum bending moment, because maximum bending moment is lie between C and D, and this equation is valid between C and D, right? So from here you can get the maximum bending moment, and this will come out to be 205 kilonewton meter. Solve it and you will get the value as 205 kilonewton meter. So this value is 205 kilonewton meter maximum bending moment, right? So this is how we can draw the shear force diagram and bending moment diagram for the given simply supported beam, which is loaded with UDL and simply supported supports, right? point loads, and then we can also find out the maximum bending moment, because the failure take place due to this maximum bending moment, right? So this is how we can solve this question.